A voltage regulator circuit design example with current foldback feature is analyzed and discussed in this video. This voltage regulator is implemented with one Zener diode, for example 4.7 volt, one operational amplifier, a Darlington bipolar junction transistor pair, and a single NPN BJT transistor as a part of the foldback and current limiting feature that relies on the transistor, a voltage division between R1 and R2, and a current sensing resistor that is a small resistor but high power. We want to see how this circuit is working, and then we would like to select the value of the components involved, these resistors in the circuit, so that we achieve the target and desired performance and KPI, or key performance indicators. Notice that the supply voltage at the input of this circuit is unregulated and varies from 11 to 15 volt, so it is changing a lot. That supply range, I'm going to discuss, it's okay for the Zener diode, but it's not okay to be directly applied to the RL as our load. What we want from the circuit output is a stable Vout voltage equal to 10 volt for the range of the current that we want the regulator to support, that RL can receive from the circuit. Okay, so the target is output 10 volt stable, and we want to also limit ourselves to a Darlington BJT transistor as an example with a maximum power of 5 watt, let's say. Okay, so and also as a guideline, we want R1 plus R2 to be 10 kilo ohm, and we want RA plus RB to be also 10 kilo ohm, so large enough so that we can practically neglect the current flowing through R1, R2 and flowing through RA and RB compared to the current, that nominal current that the load is taking from the circuit. So basically the effect of RA in series with RB and the effect of R1 roughly in series with R2 is negligible compared to operation of RL. Okay, so how do we design the circuit? Okay, so the way the circuit is working is first establishing a reference voltage, sort of accurate enough a reference voltage like a band gap, that is done by this simple combination of a series of a resistor 2K with a Zener diode that has good temperature coefficients. For example, let's say for 4.7 volt we can rely on a diode from Vishay semiconductor, like for example, consider, there are many options of course, but one example is from Vishay semiconductor, and this 1N5230 part number provides us with a good Zener diode with a good range of operational current in the range of say nominal 0.25 milliamp to 20 milliamp, and then a very good temperature coefficient of 0.03%. So this means that every degree C, if the nominal voltage is 4.7, the change in the nominal voltage of 4.7 for the diode, for the Zener diode, would be on the order of 3 10 to the power minus, so this one is 3 10 to the power minus 4, and per degree C. So every degree C, this is the amount that we will see a change, and it's a positive temperature coefficient, so it means that every degree C increase correspond to this amount of increase in the Zener diode voltage. So it's very small. That's a good feature for this diode. So that means we have a stable 4.7 volt that is relatively constant for the range of temperature in mind. Okay, how does this establish the voltage at the output? This 4.7 volt establishes the voltage at the positive input terminal of the op-amp. Assuming op-amp is properly biased, which is the case, as you can see that the top rail is connected to the unregulated 11 to 15 volt supply, which is good enough for us, and the bottom rail is connected to ground. And also the output of the op-amp involves connection to the output of the circuit and a loop back to input negative terminal or inverting terminal, indicating a negative feedback in this circuit. As an example, when positive voltage goes up, op-amp tries to increase the output, which means the output of op-amp, and then which means effectively Vout should go up to compensate, which means then this node will go up, and that would effectively increase the voltage at the negative terminal as well, trying to catch up. So that's an indication of a negative feedback in this circuit. Okay, so with that, meaning proper bias of op-amp and also negative feedback, we can make the assumption that op-amp is operating in linear region, and as a result I can say op-amp is not saturated. That means the virtual short is valid for the op-amp, which means voltage at the positive input terminal is equal to the voltage at negative input terminal for op-amp. That means if we establish, with the proper bias of this Zener diode, if we establish 4.7 volt here at the positive terminal, then that should also enforce by the negative feedback at negative terminal as well, which means it is going to appear via this wire at the output. So here we will have 4.7 volt as well. Okay, so then knowing that there is effectively practically no current going or coming out of the in or coming out of the input terminal of the op-amp because of effective infinite impedance, we can say RA and RB are in series, and therefore since this node is Vout, therefore we can just say relationship between Vout and 4.7 is just a voltage division between RA and RB. So I'm going to set the value of RA and RB such that Vout is 10 volt as desired. So we can say 4.7 volt as a voltage division is equal to RB over RA plus RB, and we have times Vout. Okay, so we know RA plus RB desired is 10 kilo ohm. So I'm going to just use that and say that this means 4.7 volt is equal to RB divided by 10K times 10 volt desired. So the outcome of this obviously means RB should be equal to 4.7 kilo ohm. And therefore using RA plus RB equal to 10K, so using that we can get RA, this means RA should be equal to 5.3 kilo ohm, so that the sum of RA and RB is 10 kilo ohm. Okay, so this is how we find RA and RB. Now let's examine what needs to be done for, say, resistor R, the current sensing resistor, and also the R1 and R2 feedback resistor for the current foldback. Okay, so in normal nominal operation, when the current that is taken from that is being provided by the Darlington pair here, which is the high power pair, especially this transistor, if the current is within the right range, this transistor should be off, and the supply is basically regulated supply is just providing a current to the load like this. But if load becomes too little, so if we, for example, reduce the value of RL too much, so let's say this becomes too small, it tries to draw a considerable current from the transistor while keeping Vout as 10 volt, and then at some point the circuit would not tolerate that, and that turning point is defined by this combination here when they turn on this BJT current sensing transistor. So in order for it to turn on, we need to consider the threshold voltage of, let's say, for the base emitter VBE of the voltage of base emitter for this NPN BJT, the threshold is 0.6 volt. When the voltage drop between the base and emitter of this transistor becomes 0.6 volt, it turns on and would start taking out current. So would start diverging the current from the output of op-amp downward and basically limiting the current that is going to the base of the Darlington pair, and therefore limiting the output current as well. So that's the plan. So let's see how this is working. So to find the right value for these guys, we need to rely on this aspect, that the maximum target power consumption for the Darlington, and especially this transistor, that is the major transistor here, the power transistor, it's going to be 5 watt. So worst case scenario, given the unregulated supply, the maximum value of supply unregulated is 15 volt. So in worst case scenario, here we have 15 volt, and at the output Vout, which means roughly at, let's say, we can calculate that, but basically the idea is, let's write and find what is the the value of voltage here, and then what is the value of voltage here, and then from there figure out what's going on. The voltage drop across R for the maximum current in the circuit is going to be negligible. So from the perspective of power consumption for this transistor, we make the assumption that we talk about V out at say 10 volt. So 10 volt basically here, and then that means we have about 5 volt drop across the collector and emitter of transistor, let's say T1, and this is T2, and this one is T3. So what I can say, power of T1 max, which is the dominant power consumption in the circuit, is limited to 5 watt. For one scenario, which is nominal operation, when output is 10 volt, we can see it's max, so it's instantaneous power. We're talking about voltage of collector emitter times the current of collector emitter, which is the max current. So this voltage in the worst case is plus minus 15 minus 10, as I said, because this drop across R is very minimal. So approximately this is the same as V out in the nominal operation. So it's going to be 5 times, and the current is the maximum current we can tolerate, so that we limit to 5 watt the maximum power consumption. So it will be ICE, or basically just Imax. So 5 watt equal to 5 times Imax. So this one is 15 minus 10, which is 5 for VCE. From here we get this result that Imax is 1 amp during the nominal operation. Now consider another scenario. By mistake or by test, for the sake of testing the tolerance of this regulator, we short the output to ground. Basically we force V out to be 0. That's the worst we can do. If that happens, then suddenly the voltage drop across the collector emitter of this transistor number 1 is going to be, worst case, 15 minus 0. So it's going to be 15 volts. So another scenario that I want to consider is, again, we don't want more than 5 watt, but now VCE of transistor 1 is 15 minus 0 times ICE. So this was 1, now 2. So in this scenario we have 15 times Imax when V out is 0. This is when V out is 10. So in this case, so when V out is nominal 10. So basically we are in nominal operation. This one here is not nominal operation. It's sort of when output is shorted. Imax is 5 watt divided by 15, which divide by 15 volt, which means Imax is, so 5 watt divided by 15 volt, which means is 1 over 3 amp. This Imax is for V out when V out is shorted. Okay, so I'm going to use these two outcomes to figure out the value of these resistors, given that I already know that the R1 plus R2 is limited to 10K desired. So let's then find the requirement to get 0.6 volt threshold for the voltage of base emitter of transistor T3. So I can say voltage of base emitter of transistor T3 is equal to voltage of base minus voltage of emitter of that transistor, which means voltage of base is this voltage, which is, let's say, V emitter of transistor 1. So we can calculate that. But then, assuming that R1 and R2 are limited to 10K, then we can say that the current that is flowing through these two guys is going to be considerably larger than the current that the base of this transistor will take when it turns on. So we can make the assumption R1 and R2 are roughly just in series. And therefore, voltage of the base for T3 is going to be just the voltage division between R1 and R2. In this case, will be, so for voltage of, let me put it this way. So for voltage of base, I can write R2 divided by R1 plus R2 times voltage of emitter 1. But voltage of emitter 1 is also equal to voltage of output plus the max current, Imax, times the resistor that will give us the voltage drop across this current sensing resistor. So Vout plus the voltage drop will give me VE1. And that's exactly what I am writing here. So R times Imax. And that is for VB3. What about V minus V emitter 3? Well, via this wire, the emitter of the T3 is connected to simply output. So V emitter 3 is equal to Vout. Therefore, minus Vout. Okay, so we need this to be equal to roughly 0.6 volt, the threshold that we need to set the circuit for the current limiting or current foldback feature. So this is the kind of equation I need to trace, and to just clean it up, I can further simplify this portion with minus Vout, and what I get is finally this. I get R2 R times Imax minus R1 Vout divided by R1 plus R2 is equal to roughly 0.6. Okay, so this is the equation that we need to have in mind, and let's refer to this as equation 1. What I'm going to do is I am going to apply this equation 1. So I am going to, let me just move this down so that there is enough space. Okay, so what I'm going to apply is now try these cases, case 1 and case 2, applied in equation 1. So I would say when Vout is equal to 10 volt, Pmax of the Darlington transistor should be 5 watt, and we found that Imax as a result should be 1 amp. By the way, for transistor there are many options, but one potential good choice, I mean there are many options. One potential example is from onsemi, semiconductor manufacturer. So in this case, for instance, I'm talking about this Darlington transistor that you can see here. So part number, say, MJE270 NPN Darlington transistor. They also have the PNP version, but for NPN1 you can see that this transistor is more than what we need, because it can tolerate the, let's say, 15 volt voltage drop across collector emitter, and more than that. It can actually go to much larger than that. Collector emitter voltage can be as high as 100 volt, and then it can go up to 15 watt, but we need to be careful about the description and requirement for the casing, the temperature of the casing. If limited to 25 C by, say, proper power dissipation planning and heat sink planning, then this can tolerate up to 15 watt. That's this transistor is good enough for the purpose that is the purpose of this circuit. There are many options though. I just wanted to show one potential option, which is this NPN Darlington transistor. So with that in mind, let me just do a quick calculation to show how we can find the remaining components. So I'm gonna apply this into equation 1, and if I do that, then the outcome is this. Of course, R1 plus R2 is also 10K, so I can take care of that as well. So with that and the knowledge that R1 plus R2 is also 10 kilo ohm, then we can say R2 R Imax is just 1 amp in this scenario, so 1 amp minus R1, and Vout is 10 volt in this scenario, so times 10 volt. 10 volt is equal to 0.6, and then we have times R1 plus R2, which is 10K, so 10K. Well, the other outcome is the scenario in which we are saying I'm going to write it here. So we are saying when Vout is shorted to 0 volt, then we still want Pmax not going above 5 watt, and in this case Imax, as we computed earlier, here should be limited to 1/3 amp by the circuit, by the current limiting feature. So again, knowing that R1 plus R2 is 10 kilo ohm, and using 1, I'm gonna apply these things into 1, and if I do that, I get R2 times R, this time 1/3 amp for Imax, minus R1, V out is 0, equal to still 0.6 10K. So what do I learn from this? I get this outcome from so this goes away because it is multiplied by 0, and I get this outcome. R2 times R is simply 1.8K, sorry, 18K, because it's 3 times 0.6 is 1.8 times 10 is just 18K. Of course, it's 18K squared, so it's not because it's 2 resistor multiplied, so we need to be careful about the dimension. But maybe the best thing I can do is I just keep it this way to avoid confusion. 1.8 times 10K. So let's keep it that way. But be careful that be careful about the dimension here, because here we have the 2 resistors multiplied. What I'm going to do is now I'm going to substitute. So this is equation 2. I'm going to substitute for these 2 values in equation 3. So let's refer to this as equation, let's say 3. So using the outcome from equation 2, I get 1.8 times 10K minus R1 times 10 volt is equal to 0.6 times 10K. So in this case, obviously what I get is R1 times 10 is equal to 1.2, and as a result I get this outcome. R1 should be equal to 1.2 kilo ohm. Okay, since I know that the sum of R1 plus R2 need to be 10K, so I'm gonna put it this way. I know R1 plus R2 is 10 kilo ohm, therefore R2 has to be 8.8 kilo ohm. So we found the values of these 2 current feedback or current sensing resistors. Okay, now we need to just apply, let's say, R2 into this equation 2 and find the value of the current sensing or current limiting resistor R. So let's refer to this as so I'm going to use it this way. From equation 2, knowing R2 is 8.8 kilo ohm, we compute R to be approximately 2.05 ohm. So if we calculate that, that's the amount we end up computing for this resistor. So it's, and we can of course compute the power, because that's the value of resistor R, which is this small current sensing or current limiting resistor. Now the maximum current flowing through this resistor is the 1 amp that we computed. That's the max. So one calculation we have is Imax, the largest amount is 1 amp. So therefore the power max of this resistor, so P max of R is equal to just 2.05 times 1 amp squared. So we have basically the outcome is just 2.05 watt. I would say maybe we select the power, let's say spec for this resistor on the order of 2.5 watt to be safe, and then that would be the resistor we need to select with the amount of roughly 2 ohm. So we found the value of this resistor as well, and that's the last component that we needed to figure out, because we found earlier the value of RA and RB, And also now we found the values of R1, R2 and resistor R. The NPN transistor is just a nominal transistor with a just nominal beta of 100. The PNP one is the one that at least can tolerate Pmax of 5 watt, as we discussed, which one option, as I said, is from on-semi or on-semiconductor, as I showed. I hope this example is helpful in terms of showing how we can, let's say, design a simple voltage regulator with current foldback, and how we can find the right values for the components given the target output voltage and the Pmax for the Darlington transistor. I hope this is helpful. Just one last thing for the foldback feature, if the plotting of the voltage is desired, effectively the way the circuit is operating is this way, that if we plot V out of the circuit as a function of the current drawn from current, let's say we set RL to reasonable values. So as we set RL to reasonable values, circuit provide V out of 10 volt with a reasonable current. As we start reducing RL, the output current is increasing and it goes up to the point that is 1 amp. And after that, the current foldback or current limiting feature kicks in. So it's as if at the beginning voltage of V out is 10 volt. As the current is increasing because of, let's say, reduction of RL, the voltage remains constant up to the point that we hit the current of 1 amp. As soon as we hit that limit, then the foldback or current limiting feature kicks in, and start from that point on. If you still keep reducing RL, the circuit cannot anymore keep the output voltage at the 10 volt level, and the foldback feature would actually start reducing the voltage. And at some point when we get to worst case scenario of output shorted, the current will get to, say, 1/3 of an amp, as I showed here. So as I showed here, 1/3 of an amp, which means the foldback feature will get to, let's say, here, 1/3 of an amp. And this is the way that foldback is working. Basically, the V over I characteristic of this regulator supply looks like this. Stable, stable, stable at 10 volt as we are reducing RL and therefore increasing the current up to 1 amp. After that, further reduction in RL, the circuit cannot 10 volt anymore. The output start voltage wise going down, and the current, as we reduce RL further, start going down. Worst case scenario, when RL is 0, we get 1/3. We get 1/3 amp, and the output voltage is 0. So this is the foldback feature that is supported by this circuit. I hope this example is helpful. Thanks for watching.